In this module, I want to define exactly what we mean by velocity. Now, up till now, we've dealt a lot with trajectory, which in vector form is a vector function of time. And if I draw one of these trajectories with a coordinate system, it can have really some arbitrary shape. And with these trajectories, we've looked at things like motion diagrams, which are sort of snapshots of different positions along the trajectory. And with those motion diagrams, we've looked at displacements, the differences between the positions, and then the average velocity, average acceleration. But the reality, we have a continuous function of time here, this trajectory. And so I could write out that position in time, that vector function, and it can have an x component, which is a continuous function of time, plus a y component that is a continuous function of time. And at the moment, these functions could be arbitrary. For example, this function might be some sort of polynomial. I'll put 3 plus 5t cubed, say, and that's the x component function of time. And the y component function of time might be 2t plus 4e to the negative 7t. I think again, sort of making these up, don't necessarily represent this graph, but they could be any functions of time. So once I have this, I can now define what the velocity is. And I'm going to define it in words first. The velocity is the time derivative of the trajectory. Now, we often call the trajectory the position. Is just really another word for it. The position function of time is the trajectory. So you can say the velocity is the time derivative of the position or the time derivative of the velocity. And now we can represent that with many equations that we want. And so in the vector form, I could say the velocity function then is the time derivative of the position. Now I'm going to box this equation here because this really does represent one of the fundamental relationships that we're going to be discussing in this course. We might derive a lot of equations for certain examples, but this is now a very fundamental relationship between position as a function of time and velocity as a function of time. However, the best way to memorize this relationship is in words, and then we can represent that any way we'd like, depending on the problem we want to solve. So let's say we want to calculate this velocity for the position function we have up here. So let's do that. If I have some velocity function of time, it's going to be the time derivative then of our position function of time, which is going to have an x component function of time, plus a y component function of time. Now, the derivative is a linear operator and is distributive, so this becomes the time derivative of the x component, I hat, plus the time derivative of the y component, j hat. And these here then become the y, but the x component, of course, sorry. The x component of the velocity, that is a function of time, plus the y component of the velocity. And so if we are only in one dimension, so in 1D, for example, where we just work with the components, we might write that the x component of the velocity is just equal to the time derivative of the x component of the position, where before then the minus sign tells us what direction the vectors are, but we don't in fact use the vector notation a lot of times if we're simply in one dimension. And so depending on the problem, we might represent this different ways, but the fundamental rule is always the same. So so let's just do an example. If we were to take this position function that we had up there and calculate it, we can. So here we had r, we'll rewrite it down here, is equal to 3 plus 5t cubed plus 2t plus 4e to the minus 7t. And yes, this is one of those completely contrived examples. I can't imagine a physical system that would have this sort of trajectory, but it's useful to practice with. So then, if I were to calculate this derivative, then I'm going to calculate the derivative of each part. So the first, I have to differentiate this polynomial, and I differentiate each term of the polynomial then. The derivative of a constant is 0. The derivative of 5t cubed, bring the 3 down, times 5, t squared, 3 minus 1, so this is I hat, plus the derivative of each of these terms. The derivative of 2t is just t, 2, t to the 0, plus 4, the derivative of e to the x is e to the minus 7t, times then the derivative of the exponent, which is negative 7t to the 0, and this is all j hat. So now I can complete this. So this is 15t squared I hat plus 2 minus 28 e to the minus 7t j hat. So assuming you're up on your calculus, this is all straightforward. You'll see I've completed some of the steps of the derivatives. We've done the standard rules for differentiating polynomials, as well as an exponential and a little bit of the chain rule used here to differentiate e to the minus 7t. So you recall in the last one of the previous modules, we took a look at uniform motion in 1D. So how does that relate to our fundamental definition? Uniform motion in 1D, just as another example. So before we had x of t is equal to some initial position plus a constant velocity times time. So if I were to apply our fundamental definition, this is equal to the derivative then of our position as a function of time. So I have to differentiate this term here. The derivative of constant is in 0, plus the derivative of this term is just linear in t. The time derivative just gives me the constant term. And we have that the velocity being a constant satisfies, or I should say we show that the velocity is a constant using our fundamental relationship between the velocity and the position. Before we complete, it's very useful to take a look at this motion in graphical form, sort of position versus time graphs. So if I plot here, this is now one-dimensional motion. So I'm only in the x-axis. But instead of plotting x and y, I just have one dimension, and so I'm plotting the x motion as a function of time. And so if I have some arbitrary motion like this, I can use our knowledge of the derivative to be able to extract velocity information from a position versus time graph. So we know that the velocity at any point is equal to the slope of the tangent line at that point. And so if I have a curved trajectory in position versus time that looks like this, I can say here velocity at this point is equal to the slope of the line at that point, and the velocity at this point is equal to the slope of the line at here is 0.2, 0.1, and 0.2. The slope of the tangent line at point 2 is steeper than the slope of the tangent line at point 1, and so the velocity at point 2 is larger than the velocity at point 1. And so we can see by this curved position versus time graph that the velocity is positive in both cases, positive slope, and increasing. And so we can use these types of graph to extract physical information about the system. Okay, for example, let's look at what a position versus time graph is for the classic throwing ball up in the air in a straight line and having it come back down. Okay, throw ball up and down. What does that look like in position versus time graph? So here's time, here's position. If we say this is 0 where it leaves, I want positive x going up, and so the ball starts at 0, and it starts with a large velocity, and it slows until the velocity becomes 0. Position gets to its peak, and then the ball comes back down. This is where you catch it. Now remember, the ball is not being thrown. This is not a position axis. This is a time axis. The ball is only going straight up and down. It's only traveling along the x-axis. But as a function of time, x is growing until x reaches a peak, and then it falls until x reaches back to the position where it started. And so if this is the position versus time graph, you can see how we can extract the velocity information as well. The slope is positive and large immediately after it leaves the hand, and it starts to slow as it goes up further. The slope of the tangent line is shallower, so it's slowing down. At the very top, the slope of the tangent line is horizontal, which is 0, and that tells us the velocity is 0 at the apex, at the highest point. And then, as it turns around, the velocity goes negative, because now the velocity is down in the negative x direction as I've defined it in our coordinate system. And then it continues to accelerate, and we can see that as the slope of the tangent line gets steeper. And so this definition here gives us the important relationship between the velocity and the trajectory, and we can use that to develop mathematical relationships between the position and the velocity. And we can also use then the information that we know about the derivative to be able to extract information about the trajectory and the velocity from these sorts of position versus time graphs as well.